Now we will finally finish the lectures on cyclic groups by finishing the proof of our last results and applying it to modular arithmetic and to the circle of fifths. Alright, now we're going to focus on the second result. So suppose b is of the form a to the k. Although actually, for the sake of the proof, it's probably easier to use m, as we'll see. Then the order of b is n over the GCD of n and m. So for instance, suppose n is 10 and b is a to the fourth. Then look at a to the fourth, a to the 8th, a to the 12th. But remember, a to the 10th is the identity, so this is equal to a squared. A to the 6th and a to the 10th is the identity, and look, you had 5 elements. And what is the GCD of 10 and 2? 10 and 4. It's 2, and 10 divided by 2 is 5, and we have 5 elements. And so the order should be 5. Or more accurately, once we hit the 5th power of a to the 4th, we get the identity. So this seems to be true. Well, how do we prove it? Let me try to use this previous theorem. Remember, this is an if and only if. So the point is, if you can find this n that works, remember it has to be the common divisor of all the powers that give you the identity. That's one of these things you can get from here. What do I mean by that? Is that if you find an integer n that has this property, then it's going to have to be the order of your cyclic group. So, let's let d be the GCD of n and m. Then n is going to have to be q times d. And m is going to have to be r times d for integers q and r. Moreover, q and r themselves can't have a common factor because, well, if they did, then d wouldn't be the greatest common divisor. There'd be something even larger. Well, let's look at a to the k equal to the identity. And this is where k has to be a power, or I should be more careful. So we're looking at a to the m, and we're looking at powers of it that are the identity. Well, according to our previous theorem, the only time that happens is when n divides m times k. But n is equal to q times d, and k is equal to r times d. So we're saying that this happens if and only if n divides m times k. That only happens if and only if qd divides r dk. I imagine you can see that you don't need the factor of d, so this only happens if and only if q divides r times k. Well, q and r have no common factors, so the only way q can divide r times k is if q divides k. That's a number theory result that you can try to prove. And so we see that the only powers of k, of a to the m, that give you the identity are ones that are multiples of q. And so we see that the order of b is q. If it's got any order at all, it has to be that one. And then you can see that that's the one that has to work, because then you can just check that a to the qk is the identity. And so a corollary of the previous results is that an equivalence class in the group of congruence classes modulo n is a generator for the group of congruence classes modulo n if and only if a and n are relatively prime, which means they have no common factors. And A, in general, has order n over the GC. Well, I mean, the proof of that is that A has this order, according to the previous result. And the only way that order is equal to n is if that GCD on the bottom is 1. And so, for example, if we let n equal 12, then the generators, you're going to be looking for numbers that are between 1 and 11 with the property that the GCD of I and 12 is 1. Well, what are the divisors of 12? The divisors of 12 are 2 and 3. Well, prime divisors are 2 and 3, and then other divisors are 6 and so on. And so you're looking for numbers that are not divisible by 2 or 3. And so your options are 1, 5, 7, and 11. And so there are 4 generators for Z mod 12Z. And the first one corresponds in music theory to just increasing by 1 semitone. And the last one would correspond to decreasing by 1 semitone. So those two are not considered that interesting, but the plus 7 is actually, as mentioned before, that's the circle of fifths. So you see the circle of fifths comes from this theory. And the plus 5 can also be viewed as is often viewed as actually subtraction instead. So let's go in the circle of fifths, but backwards. And so we see that the 4 generators actually all pop up in music theory. And the point here is that if you take any other element, like say plus 2, you'll get only some of the elements. You're not going to get all of them. So these are the only 4 combinations you can make that allow you to get all 12 semitones. And all other ones you're going to get a proper subset.